Chapter 2.4, as it says up here, normal curves, part 2, or normal distributions, part 2. Yesterday, we were just taking a look at what a basic normal curve is all about, defining what a z-score is, how many standard deviations your score is away from the mean. What we do now in the second part here is we apply it even more, okay? So we're going to actually take you through what we call a 4-step process, okay? If you've seen problems, like even in chapter 1, I think I might have assigned 1 or 2 problems where it says do the 4-step process. I'm going to show you how you do this with all of these problems here, or most of these problems here today. So in your notes where it says steps for finding normal proportions, I've kind of summarized what I do in these steps, and then I'll demonstrate them for you. So the first thing, right, that they want you to do is basically state the variable you're trying to find. So state x, what x is. So define it. Tell me what you're actually dealing with. It would be helpful and beneficial for you, but you don't necessarily have to write the notes down, but when you go back to do the problems and work on them, it's always nice to have good examples. Plan. The second thing you do is define what you're finding. Okay. So not just what x is, but what you want to find for x, and how or what you will do to find it. Right. So you kind of put your plan together. Everybody, lots of students like to jump to step 3 right away. They do the do. They solve for x showing all your work. Okay. They like to figure out, they just like, oh, I got to find out what the answer is right away. But it's so important in statistics, stating what you're trying to find, okay, and showing all your work. Then finally, what we like to do in statistics, which is kind of new in math, because in math you always just say x equals something. We actually write our answer in a sentence. Write the answer to the question in a sentence. So what we're going to do today is the next pages of notes just have a few example problems that we're going to take you through this process. And I'll write them step by step, and I'm hoping that I'll at least put them color coded so that when you see them, you know what step I'm actually on. So I know I see some of you still writing, so give me a minute or so. Make sure you're getting these steps. Alright, are we okay? Alright, let's take a look at then our first example problem. Number 1 says the distribution of scores on the SAT. I know that many of you, actually almost all of you, if you were here last year, took the ACT, but we're going to talk about the SAT, another standardized test. Are approximately normal with a mean of 500 and a standard deviation of 100. Lots of times when I read a problem and I see the mean stated, I like to write the symbols right by it. So right away I'm just going to note those. Ooh, there's my population mean. There's my population standard deviation. Okay? It says normal. So I know it's, we're talking like a normal curve with a mean of 500 and a standard deviation of 100. That's going to be important information that we will be using. So now in part A here it says draw a normal curve, identifying the mean and scores that are 1, 2, 3 standard deviations away from the mean. This one I'm not going to do the state plan do conclude piece, because there's no reason to, we're just drawing a curve. So, your best of your ability, draw your normal curve. Ooh, that one's a real long one with long tails.
Nice.
Right smack at the peak, I put my mean of 500. So roughly where the curvature changes, that's 1 standard deviation. So I'm going to try to keep this distance here the same, 2, 3, and then I'd use that distance going backwards, 1, 2, 3. So now our standard deviation is 100, nice numbers to work with. So I'm just going to add 100 and subtract 100 from my mean. So now I'm at 600, 700, 800, going backwards, 400, 300, 200. What's nice about doing this part A piece is drawing a normal curve, labeling it, kind of gives us a picture of what the distribution looks like. Looks like, almost, 99.7% of my scores are going from 200 to 800. So almost my entire distribution has that as an interval for scores. Alright, so then for part B, this is where I'll start doing the 4 steps. It says, what proportion of students scored above 680? So, in the state, I'm going to define my variable. So I always like to say what x is. So I'm going to say let x equal a student's score on the SAT. That's all I have to do for the state part, define my variable. For the plan, I gotta tell what I'm trying to find and what I'm either gonna use or how I'm gonna find it. So, I want to find, and I'm gonna start using some notation. It says I want to find proportion of scores above 680. So if I think about how we like to represent a proportion, we'll do that with a capital letter P. We'll use that for like proportion or percent or probability. I want to know what proportion of, so I have a parentheses, of scores. Okay, well, we're talking student scores on SAT, that's my variable x. That's above 680. That's greater than 680. This is what I want to find. Okay. Now, what are some pieces of information that I know or I'm going to use? Well, where our distribution is normal with a mean of 500 and a standard deviation of 100. So I'm going to use that information to find it. So now, how I go about finding it. Guess what I'm going to calculate out next? What were we playing around with yesterday? Z-scores. So what I'm going to do is find a Z-score. So first of all, I'm just going to kind of visualize what I'm looking at. So I have a little normal curve here, and that's where this picture up top helps. My mean's at 500. I'm looking at scores that are about 680 or better. So I know that my answer should be relatively small, meaning I know for sure it's going to be less than 0.5. Now, in order to find this, I'm going to either use table A or my normal CDF function on my calculator to find it. And those involve z-scores. So I'm basically now going to ask myself, how many standard deviations is my score away from the mean? So to calculate out that z-score, again, remember the formula. I'll write the formula here, but you'll see me in the next ones not write it all the time. But I thought I'd at least write it up there so you know where all the values are coming from. So remember that z is equal to your score. Your score is what's given, 680. The mean of the normal curve, 500. The standard deviation, 100. So, if you plug that into your calculator, 680 minus 500, hit enter, you get 180. 180 divided by 100, 1.8. So what you're looking at here is, if we're looking at the standard normal curve, and a standard normal curve, the z-score is 0, and I'm looking at scores that are 1.8 standard deviations above the mean. So really what I want is the probability that my z-score is greater than 1.8. That's what I really want to find. So, are you okay here with me using normal CDF in the calculator?
Yes.
Okay, from yesterday we were talking about that. So, to get this value, I go normal, CDF. So now, the two numbers, lower bound, upper bound. What's my lower bound z-score? Not 680, that's not the z-score. 1.8. I'm 1.8 standard deviations above the mean, and which direction do I want to go? To the right, so what's the upper bound? A very high number, right? Infinity. So, yeah, the 99 ... I just noticed how I went CFD instead of CDF. Anyone catch that? Because again, it's cumulative distribution function. So I had a little dyslexia moment where I flipped letters. I do that from time to time. I do, flip letters and numbers. So, alright, so second vars. Number 2 is normal CDF. 1.8 to a bunch of 9s. 2 9s, 3 9s, that's plenty. You'll get the exact same answer. And look at that. 0.0359. I go out 3 decimal places with proportions because if I was using table A, that's what I would get for an answer also. 0.0359. Now if you're actually using table A, you calculate out the area of 1.8, look on your table, and you'd actually have to subtract it from 1. So I've done the state, I've done the plan, I've done the do. Guess what I need to do last but not least? Okay, I need to explain, so I just need to write a sentence answering the question. So it's just basically restating this. The proportion of student scores above 680 is 0.0359. And that's it. Piece of cake for that corn gravy tree?
Yeah.
Well, it means it's easy. Alright, can I do the next one?
Yes.
Alright, let's do the next one together. Can I speed it up a little bit?
Yeah.
Alright. I'll try to at least speed it up a little bit, sometimes I like to go warp speed, so again, same process. I'm gonna let X equal a student's SAT score. On this one, I want to find scores that are below 420. So I want to find the proportion of X that's less than 420, where our distribution is normal with a mean of 500 and a standard deviation of 100. So now in the do, I like to draw a picture. My mean here is at 500. I'm looking at scores of 420 or less. Am I going too fast now? Okay. Speed it up, all right. So I'm calculating out Z. My score of 420 minus the mean of 500 divided by the standard deviation of 100 is negative 0.8 standard deviations, or 0.8 standard deviations to the left of the mean. So this Z score is at negative 0.8 when the mean would be 0. So really I want to find the proportion where Z is less than negative 0.8. So to get this value, normal CDF, negative infinity to 0.8 or to negative 0.8. So negative infinity, so negative 99 ... to negative 0.8. Again, that's my lower bound, upper bound. So calculator time. Second VARs. Normal CDF. I'm putting in negative infinity to negative 0.8. So 0.211, and I'll round it to 9. So then the proportion of student scores, or student SAT scores, below 420 is 0.2119. Emma.
So with negative scores, is it always going to be like the upper bound then?
Well, it depends on how they ask it, okay? In this particular one, we had a negative Z score, okay? And the reason why it's the upper bound was because I was doing a less than.
Okay.
When you do less thans, your Z score tends to be the upper bound value. When you do greater thans, like the one up top, your Z score tends to be the lower bound, or will be the lower bound.
Okay.
In D, we have an in-betweener. We like that because then we get a lower bound and an upper bound that are both Z scores.
Okay.
So lots of times it's important to know what the picture is, and which is lower bound and upper bound is really dictated by greater than or less than, not if it's positive or negative.
Okay.
Excellent question. All right, can we go to D? Okay. So how was the speed on that second one?
That was good.
Great.
Good, not too fast. All right, so again, on this one, we're gonna let X equal a student's SAT score. I know this is kind of redundant in the first steps, but lots of times if you're asked questions like this, you sometimes aren't given like 7 different questions. You might be only given 1 or 2 parts. So, the plan. We want to find, now in this one it says the proportion of scores between 370 and 650. So you write the first or the lower number first, less than or equal to symbol, your variable x, which has to be less than or equal to 650. So when you read this inequality, it's saying x is actually greater than or equal to 370, but is less than or equal to 650. Where, again, our distribution is normal with a mean of 500 and a standard deviation of 100. So I draw myself a nice little picture. So that means at 500. So now I'm looking somewhere over here at 370, somewhere over here at 650. Now again, if you're going, well, why does he know to put the 370 about there and the 650 about in its location? I go back and I kind of go back up here and say, all right, 650 right in here, 370 right in here. So that, again, that's kind of where I'm estimating them. So I use that picture on part A to kind of help me draw it. So this one's going to look fairly big, probably much more than 50%. But on this one, I have to calculate out 2 z-scores. So the first one, the lower bound score was 370 minus 500 divided by 100, negative 1.3. Because 370 minus 500 is negative 130. Negative 130 divided by 100, negative 1.3. 650 minus 500 divided by 100, you got it, 1.5. 150 divided by 100. So with this one, so I'm really trying to find the probability that, whoops, forgot the 1, there we go, negative 1.3 and 1.5. I'm trying to find my z that is between that. Asia.
Will we ever work with a curve that's not normal?
Will you? Yes. But not until the latter chapters. Right? There's a distribution called the t-distribution and the chi-squared distribution that we'll probably do near the end of term 2 that we'll take a look at. But for the vast majority of problems, they'll be normal. So, to calculate this out, on my calculator I'm going normal CDF from negative 1.3 to 1.5. So second VARs, normal CDF, negative 1.3. Oh, didn't take my 1 for some reason. Or my negative 1.3. Thank goodness I caught that now, to 1.5. What? That's not right. Something went wrong. Start again. Second VARs. Normal CDF. Negative 1.3, comma, 1.5. There we go. 0.8364. So, we can answer the question. The proportion of student scores or student SAT scores between 370 and 650 is 0.8364. All right, so in these first three problems, you did a less than, you did a greater than, and you did an in-betweener, just like what you could potentially see. Question E is one where, as we saw yesterday in yesterday's notes, where you have to sometimes work backwards to get your answer. So in E it says, what SAT scores would place you in the middle 90th percentile? So on this one here, okay, the process that we'll still do the steps, but what we're finding is a little bit different. So we're still going to let X equal, okay, a student's SAT score. So on this one, what we have to do is we have to find two X values that mark the middle 90% of SAT scores. So what I'm going to do is I'm going to actually put the drawing here in my plan. So what I'm talking about here is, here's my normal curve. I'm looking for a lower bound X score and an upper bound X score such that this area in the middle is 0.9000, or just 0.9. I put the zeros just because in table A it's 4 decimal places. So we will, guess what we need to find to help us answer this question? We're going to need to find the corresponding, here we have, to find these X's, what would we be able to find first from this area?
The vars 3, what is that called?
So if I think about here I got an area. What did I get my area from?
Z-score.
Z-scores. So I'll need to find the corresponding Z-scores. So what calculator function helps us find Z-scores from an area?
Vars 3.
Okay, the inverse norm. So now I'm going to do the do. So remember that if we go inverse norm of an area, we get the Z-score. Now here comes the challenge. What's the two areas that we should actually be using? What is this area to the left of x1? And what is this whole area? Well, how much is these two areas combined?
1.
Okay. Well, the whole thing is 1. 0.1. So if it's symmetric, how much is each? 0.05. 0.05. Okay. So x1, that area is only at 5%. So we go inverse norm of 0.05. So on my calculator, second bars, number 3 of 0.05. I get negative 1.6448 ... With a z-score, I just rounded to 2, negative 1.65. So what it's saying is, the lower bound score is negative 1.65 standard deviations away from the mean. Okay. What value would I use for the upper? How much? What's the area below this line? What's the area? 0.95. Because you have the 90% and the 5%. So if I do inverse norm of 0.95, I will get positive 1.65. Anyone want to venture a guess why it's just the positive value?
Because there's 5% of the range.
Okay, 5% left on each side, so they're equal distance from the mean. It's symmetric, so they should be just opposites of each other. So now we got our z-score. I'll continue my work up here. So now I want to find x. So I have to find x. I know that a z-score is equal to my score minus the mean divided by the standard deviation. Do I now have a z-score?
Yes.
Sure. Which one do you want to work with first? The negative or the positive?
Positive.
Alright, most students like to work with the positive first, which is just fine. 1.65, that's my z-score. What's my x? Do I know it? Isn't that what I'm trying to find?
Yes.
So it's the x1 value. So that's x1. What's my mean? What's my standard deviation? So now I just need to solve this for x. So if I'm going to solve it for x, what would I do first? Multiply by 100. Cross out. 100 times 1.65 is equals x1 minus 500. So then what do I need to do?
Add 500.
Add 500.
665.
So x1 is 665.
You just multiply your z-score by your standard deviation.
And add it and subtract it to the mean?
Yeah.
Yes. Okay, so what Isaac is saying is this. I could take this formula right here if I wanted to, multiply both sides by the standard deviation. If I do that, I would have standard deviation z equals x minus the mean. Add the mean to both sides. And another way I could find x is just take the mean plus the standard deviation times z. So I'm going to do that for the second one. So for x2, it's going to equal the mean plus the standard deviation times z. So x2 equals 500 plus 100 times negative 1.65. So x2 equals 335. I'm just going to slide this up a little bit. It's going to jump here in a second. There we go. So I still need to, it jumped too much. So we need to answer the question.
There's no zero.
Okay. So again, it says what scores would place you in the middle 90 percentile. Scores from 335 to 665 would place a student in the middle 90th percentile. flip to the next page, there's more examples. I will let you as a class decide, do we go through number 2 together or number 3 together? Just do one of the two.
Which one's harder?
So,
Yeah, 3 is.
how many of you would like number 2? Is it 1, 2, 2 hands. How many of you would like me to do number 3? I see more hands with 3. So let's go to number 3. Alright, so we're going to skip the IQ score 1 and go to number 3 here. So, it says in 2008, so a little outdated, Wimbledon tennis tournament, Rafael Nadal, still playing tennis, averaged 115 miles per hour on his first serves. Is that fast for you tennis players?
Yeah.
Yeah, I think so. Anything going over 100 miles an hour is fast. Okay,
That's baby.
that's baby.
That's baby.
That's faster than any slap shot in hockey, isn't it?
Not faster than the fastest crossbar.
So,
It's like the fastest serve is like 130.
okay, 135. Now this is his average.
Yeah.
So,
This is baby.
assume that his distribution of first serves is normal. Ooh, normal. Good to know. Mean of 115. Standard deviation of 6. So I'm going to note those means and standard deviations. About what proportion of his first serves would you expect to exceed 120 miles an hour? Okay? So, first thing I'm going to do is I'm going to let x equal, okay, the speed of a first serve by, I'll just abbreviate Rafael Nadal, so I don't have to rewrite his name every single time. But basically, that's my variable. It's the speed of his first serve. So on this first one, I want to find the proportion of first serves, x, that exceed 120 miles an hour, where the distribution is normal with a mean of 115 and a standard deviation of 6. So I'm going to draw myself a little picture so I can see what's going on. Am I going too fast in these first 2 steps? Okay. So, I label 115. One standard deviation would be at 121, so I know that 120 is a little bit less than that, and I want all the ones that are greater than 120. So again, I'm estimating where that is on my normal curve, but I know that it's just a little bit less than 1 standard deviation to the right. So now, I'm going to calculate out a z-score. My score 120 minus the mean of 115 divided by 6. If you trust my math, it's 0.83 repeating with the 3 repeating.
It is.
So I'm just going to round it to 2 decimal places. So now what I'm really looking at is what's the probability that z is greater than 0.83. So that's equal to normal CDF. My lower bound is 0.83. My upper bound is infinity. Lower bound, upper bound. So now, second bars number 2, 0.83 to infinity, 0.2033. So the proportion of Raphael first serves that exceed 120 miles per hour is 0.2033. So 20% of the time he's serving his first serve 100 faster than 120 miles an hour. Am I going too fast? Okay. So, just to save a little bit of time, these first, actually I can't, let me,
Just write out P of X. Like,
I'm gonna, this first step would be the same thing. But, for my second step, I would say find P. In this particular case, we would be between 100 and 110. Again, where the distribution is normal with a mean of 115 and a standard deviation of 6. So this one requires you to find 2 z-scores. But what's nice about it is then you'll get an interval. So 100 and 110. Well, the mean is 115. So 100 and 110. 100 I believe is going to be way down here. 110. Looking at in between those two values. I'll move it up here a little bit. So z-score for both of them. So the first one, 100 minus 115 divided by 6, I believe is negative 2.5. Is negative 15, yeah. Divided by 6, negative 2.5. The other one, 110 minus 115 divided by 6, yeah, is the negative 0.83. So I'm really looking at the proportion of z-scores that are between 2.5 and negative 2.5 and negative 0.83. So here I'm going normal, CDF, negative 2.5, that's my lower bound. My upper bound is negative 0.83. I'm going to do the calculator here. Second bars, number 2, negative 2.5 to negative 0.83. 0.1971. So the proportion, is it percent? Oh, so we're talking about percent. Thank you for catching that. Actually says, did the previous one say percent? No, it did say proportion. So the percent of Raphael Nadal's first serves, oh, I was going to write F instead of first. First serves that are between 100 and 110 miles per hour is 19.71%. So just under 20% of his serves are between 100 and 110 miles an hour. Oh, only one more to do. Yay! How much time do I got left? How time do we get out of here at?
43.
43. 12:16. I know, long one today. So, last one here says, what is the third quartile of Rafael Nadal's first serve speeds? Meaning, third quartile is what percent? Not third standard deviation, third quartile. Quartile divides in quarters. So Q1, Q2, Q3. So we're talking about 75th percentile. So in this case, we want to find X where the area is 0.75 left of X under the normal curve, or under the normal curve with a mean of 500 and a standard deviation of 100.
Isn't it 115 in space?
Oh my goodness, yes, thank you. Why was I using SAT scores? That was the last problem, where N is 115 and 6. Thank you for that catch. After I do so many problems, you know. So, what I'm looking for here is, where is X where this area equals 0.75?
133.
So, I need to go inverse. Whoops, I'm actually doing the do part, so I apologize. I'll switch to green. I try to color code. So in the green here, I'm going to go inverse norm of 0.75, and that's going to give me my corresponding z-score. Second bars, 0.75. Oh, come on, calculator. Take my commands. 0.75. So, our z-score is 0.67. So I want X. So again, if I'm using this formula, z is equal to my score minus the mean divided by the standard deviation. You could think about it like this. If you solve again for this, X is, again, since this is your mean, you're basically going to take your mean and add however many standard deviations you are away times that z-score. The z-score tells you how many standard deviations you are away, so you times it by the value of the standard deviation to help you get X. So in our case, X would equal 115 plus the standard deviation was 6 times 0.67. So I believe X ends up being about 119. Just show, let's see, 115 plus 6 times 0.67. 119.02.
How did you
How can you do that?
How would I do that?
in your head?
0.67 is like 2/3.
Okay.
2/3 of 6, well, 2/3 of 3 is 2. 2 threes make a 6, so 2 times 2 is 4. So that's why I knew I was adding about 4 to 115. There was another question, I think. So, the third quartile of Raphael. Now I finally spelled Raphael correct. Nadal's first serve speed is about 119 miles per hour. I rounded it to the nearest mile per hour since it was so close. If you said 119.02 miles per hour, I am fine with that too. Alright, use these examples as a guide to work on your CFUs in 2.4. So the problems that you have in 2.4 are very much similar to what we just did today. So